Just has to think about it for a while. And so we had stuff like this. Derivative. Following. For my first one, let's just do a polynomial kind of guy. So let's say y is equal to 6x to the 9th plus 2x to the 5th minus 3x plus square root of 2. But one thing I want to get you to do is label your derivatives as such. Eventually, you're going to start taking higher order derivatives. We'll do that today. So I want you to label it. Since this is just a polynomial, I can go through there term by term and take derivatives. And those numbers in front, we can kind of ignore them and smack them on at the end. I call this function y, so I'm going to label this derivative as y prime. So don't just straight out equal signs here. Give me the name of the derivative right here. So let's see, using this rule, I'm just going to hang on to the 6 for a minute. And now I'm going to take the derivative of x to the 9. And this says bring the power down, raise it to 1 power less. So we have a 9 times x to the 8. Same thing with the next one, you got the plus sign, I can go through plus signs. Hang on to the 2, bring the 5 down, 1 power less gives me to the 4. Next term, I got a minus sign, so I can pull out the 3, the derivative of x to the first power, it's just going to be 1. Finally, the last term is just a constant. The derivative of any constant is 0. Sorry?
8, 4. Can you do 8, 4 is constant? Do something over that.
I'm missing it again. Right here.
Honestly,
That's too loud for me. Now let's put everything together. 6 times 9. Is that what you wanted me to do? 2 times 5 is 10. And then 3 times 1. So if you want to go from here to here, you can. I just did this step to emphasize that I'm using this rule for this. Yes,
So on the test, would you want us to separate it out like you did?
it doesn't matter. However
Okay.
you want to do it. We'll go. I mean, we'll go fast on here. I'll do the next one. Speed of that step. Sir,
dumb question. With 3x, why did it become 3 parentheses 1?
right here. What's the derivative of x?
Oh,
Oh, derivative of x is 1.
I'm looking for it.
All right, so now let's put some radical signs on these guys. Call this one alphabet. And let's put 6 times the square root of x minus. What's it gonna say? It's not.
Yeah.
That's engineering at its finest. Use the crack. How about 3 times the cube root of x? How about that? Those both represent x to a power. And so we first rewrite those as x to a power. What's the power when you see a square root sign?
1/2.
And then a cube root sign?
1/3.
Good. So I first write this as 6x to the 1/2 minus 3x to the 1/3. So this is implying that that's still f. Now I'm ready to take the derivative. So now I'm going to name it f prime. So let's kind of do this part together. If I'm pulling the 6 out and then bringing the 1/2 down, eventually I have to multiply 6 times 1/2. Let's go ahead and do that and get 3. My new power is 1 power less. So let me just put that here so you can see what I'm going to do. Take 1 away from a half. What's a half minus 1?
-1/2.
All right, we'll do it again here. I'm going to bring the 1/3, multiply with the 3, and that gives me a 1. Then I'm going to take 1 away from 1/3. What's that power? -2/3. And then it's probably good manners to write that with positive exponents. This would be 3 over x to the 1/2. I want to emphasize that the negative exponent is only on the x, so the 3 stays on top. Then over here, I'll have a 1 over x to the 2/3. If you like fractional exponents, that's good. If you like radical signs, what would that look like in radical form?
Squared. Well, it'd be just a third. Squared.
The cube root of the x squared, right? So that's 3 over the square root of x minus 1 over the cube root of x squared.
But,
If that wasn't the question.
would you also accept if we did like 3x to the -1/2 or?
Yeah, I'll take it here.
Okay.
I won't make you simplify. But there are some problems where we're going to need to evaluate this at a particular point, and it would help if we knew what those negative exponents meant. All right, next one. Let's call this guy G. Let's see, let's go with x squared over 2 minus, how about 2 over x squared? Plus a half. Oh, dang it, I gotta move it again. Our theme here in these 2 examples is we want to write things as a constant times an x to a power. So I'm going to take a minute here and rewrite all of those in that form. Like that first term, I'm going to write as 1/2 times x squared. And then the second term, I'm going to write that as -2 times x to the -2. So that it looks like what I want it to look like. A number times x to a power. Number times x to a power. And then this says we can just go through there term by term, bring the power down, raise it to 1 power less. Now I'm taking the derivative, so I'll label it as g prime. So what's the derivative of 1/2 times x squared? 1 times x to the 1, right? 2 times a half gives me a 1. 1 power less gives me a 1. All right, so here we go again. -2 times this -2 gives me a +4. And now we're 1 power less. So -2 minus 1 is going to give me a -3 power right here. And then the derivative of the 1/2 is 0. So our derivative will look like x plus 4x to the -3. We want to write that with positive exponents. The 4 stays on top. The x goes on the bottom. As we were leaving class the other day, I gave you the quotient rule and the product rule, and let me show you why we have a need for that. We have the product rule for derivatives, mainly because the derivative of a product is not the product of the derivatives. cannot go through a product and take the derivative of each factor and then multiply that together and call that the derivative. Let's do that with an easy product like x squared times x cubed. If you were to simplify x squared times x cubed, what would you get? X to the fifth. What's the derivative of x to the fifth? 5x to the fourth. So I know x squared times x cubed is x to the fifth. The derivative with respect to x of x to the fifth is 5x to the fourth. Now, if I look at the product of the derivatives here, the derivative of that is a 2x. The derivative of that is 3x squared. That doesn't come anywhere close to 5x to the fourth. The derivative of product is not the product of the derivatives. I'm going to show you what it is using the definition of the derivative on the general functions f of x and g of x. So I'm going to derive for you the product rule. You can watch this part. I'm going to find, I'm going to use the notation I did before. A first term multiplied with the second term. Then by the definition, f prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. So in our problem, I need the capital F evaluated at x plus h multiplied with the capital S at x plus h. Then I need to subtract that off as I see it. And then I need to divide that by h. Now I'm going to add 0. And it's going to be in this cute little color here. Who dat? Morning.
It's alive.
It's barely. Look at that. Is that everybody now? At 25? Sir,
When you say let f(x) equal to,
the product, just an arbitrary product.
okay,
So I'm calling this the first
That
term
is-
and the second
that
term.
doesn't have anything to do with the fact that it's, I don't know why.
I'm just going to derive the product rule, and I write the product rule in terms of my first and second factors. Okay, so I'm going to add 0 like this. Let me copy this term down.
Well,
Put that in here. So let's see. I'm going to put in and then I'm going to take it out. So you agree that's going to be 0? And now I'm going to put this on the end. And then I'm going to divide by h. Which shows this configuration, because I'm going to group these two together. And I'm going to pull out the common factor of f of x plus h. I'm going to group the remaining two together. And I'm going to pull out the common factor of s of x. So I said I'm going to pull out the capital F at x plus h. And what's left is this minus that. I've got a plus sign. Common factor here was s of x. Pull it out, and I have f at x plus h minus f of x. All of this is divided by h. So h is a common denominator to the two fractions that are added. So I'm going to put that as two separate fractions, just with my little erasing thing, like this. I'm going to put it here, and then I'm going to put it here. But it seems much more convenient if I just moved it under here. And if I move that just under there. So that's just a little bit of algebra. And now I can take the limit of each of these term by term. Yes, sir.
But how do you do that? Because why don't you get under that factorization? Still, eight.
If you multiply three numbers together, 3 times 5 times
Oh, yeah.
2. I don't do 3 times 5 times 3 times 2. I do 15 times 2 is 30.
Okay.
So I pair them up and then multiply. So I paired them up and then I'm going to multiply.
Okay.
Okay?
That's the same as f of x plus h over 1.
Correct.
Right.
You have all the ones you want. Ones are free. Now, as I take the limit as h goes to 0, this approaches f of x. What is this approach? That's the definition of the derivative of s of x. This stays here, it doesn't depend on h. That's the definition of capital F of x. And so I get that my derivative, f prime of x, is the first function times the derivative of the second function plus the second function times the derivative of the first function. So in words, the product rule derivative with respect to x of the first times the second is first times the derivative of the second plus the second times the derivative of the first. The order doesn't matter because these are added. And addition is commutative. So if you'd rather do it, take the derivative of the first times the second plus the derivative of the second times the first, that's fine. Hold one, take the derivative of the other. Then hold the other, take the derivative of the one, add them together. Let's try it with the x squared and the x cubed. So there's my first, there's my second. And so the derivative will look like x squared times the derivative of x cubed is 3x squared. Then the other way. Copy down the x cubed, take the derivative cubed, I said. Take the derivative of x squared and get 2x. Now when you simplify that, you get a 3x to the 4th here, a 2x to the 4th there, for a grand total of 5x to the 4th, which is what we should be getting. Okay? So I work lying to you. We had a quotient rule, and so we do the same type of argument with an f over an s. I do the same kind of adding 0, and you're going to get something that looks like this. Take the derivative with respect to x of a top factor and a bottom factor. It'll be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom factor squared. Let me show you why we need this by looking at our easy polynomial example. Let's, for instance, take x to the 5th over x squared and simplify it first. That simplifies to x cubed, and the derivative of x cubed is 3x squared. But if I look at the ratio of the derivatives, 5x to the 4th over 2x does not simplify to 3x squared. Right? The derivative of a fraction is not the derivative of the top divided by the derivative of the bottom. So let's take the derivative of this using our quotient rule and show that we will get the 3x squared. Not equal to 5x to the 4th over 2x. Instead, respect to x to the 5th over x squared is bottom term times the derivative of the top minus the top term times the derivative of the bottom divided by the bottom term squared. And with a little work, I want to show that this will simplify to our 3x squared that we would get if we simplified initially. So let's multiply the top out and combine like terms. This is 5x to the 6th minus 2x to the 6th. Downstairs I have x to the 4th. So there's a 3x to the 6th over x to the 4th, and by golly, that's the 3x squared that we know we should be getting. Now notice that in the quotient rule I have a minus sign and subtraction is not commutative. So you have to do the derivative in this one. You have to take the derivative in the quotient rule in this order. Bottom times the derivative of top minus top times the derivative of bottom. Here you have the option, since we're adding, you can do any order. Subtraction. So, the product rule problem up here, the quotient rule problem. Find the derivative with respect to x. Let's see, let's put x to the 4/3. That's 3x multiplied with 10x to the 4th plus x minus 2. So I've given you a product, and if we wanted to, we could multiply it out and we would get 6 terms added together, and we can take the derivative term by term. But we now have the option of taking the derivative by just leaving it as a product and using the product rule, and that's what I'd rather do. When I use this notation, then my next line would have an equal sign on it, because it says take the derivative of blah. So when I take the derivative of blah, the derivative is, so there's my verb. So here's my first, here's my second, the way I've written down, I copy down the first one just as I see it. And now I take the derivative of the second. So just to show you I'm taking the derivative, I'll use a square bracket. What's the derivative of 10x to the 4th? 40x to the 3rd. What's the derivative of x?
1.
And what's the derivative of 2?
0.
There's the derivative of the second. Now we copy down the second one. 10x to the 4th plus x minus 2, and take the derivative of the first one. What's the derivative of x to the 4/3. So this power is going to be 4/3 minus 1.
Which is 1/3.
4/3 minus 3/3 gives me a 1/3 right here. Plus 3, the derivative of x to the first power is just 1. So that's all I get there. Now, if I was too lazy to multiply this out, I'm certainly too lazy to multiply that out. So I'll leave my answer there.
Nice. Wait. Do you have to simplify it now? Do that?
You don't have to. It's America. You can simplify if you want to. Yeah, because you are still learning algebra. I'm going to trust your algebra skills. That's right. And then I have to read your junk, and I don't want to read your junk. I'm only thinking of you. All right, let's try a quotient rule problem. Let's take the derivative with respect to x. Let's put a 4x plus 1 over an x squared plus 2. So I'm going to show you what I'm going to do. I'm going to do the bottom times the derivative of the top minus the top times the derivative of the bottom squared. Put it right here. Here's the bottom, x squared plus 2. Now as you come in, the derivative of the top, 4, that's it, minus the top times the derivative of the bottom. Go, go, go. 2x over the bottom square. I am going to simplify this one though, because many of you are going to be tempted to see that one looks like that one, so I want to cancel. Can't do that, can you? Can't cancel because this bar acts as parentheses. There's not a common factor of x squared plus 2, so you can't cancel it. So don't be doing that to me. Those will always look alike, so don't cancel it. We simplify on top by doing the multiplication, and then we'll collect like terms. Looks like I need to do that over here.
I have another question.
Yes, sir.
So you said derivative of x equals 1, so 4x would be 4, right?
There it is.
But if it's 4x, 4 plus 1, would it not be 5?
No, what's the derivative of
Oh,
a constant? Derivative of constant is 0. All right, so here we go. I'm upstairs and I'm distributing the 4 through the parentheses. And so I have a 4x squared plus 8. Now I'm going to distribute 2x through the parentheses and the minus sign. 2 distributions at one time. 2x times 4x gives me 8x squared with a minus sign. 2x times 1 is 2x. Now the minus sign gives me a minus 2x there. There's no reason to multiply the bottom out. Just leave it as a quantity squared. There's no reason whatsoever to multiply that out. The top simplifies. I get a minus 4x squared minus 2x plus 8. Might want to pull out the even number and maybe even a -2 and then see if you can factor what's left, but there's really no reason to do that either. So let's just say we done. That's it, that's all. You guys have a little song to help you remember the quotient rule?
I just remember it like there's like a parabola this way because for the product rule, it's like a parabola this way. And it starts with the normal number, then it goes to the derivative, and it's positive, so it's added, and then another derivative to the x, a normal one, and then for the quotient, it's the other way. So it's derivative, and then it's the x, and it's negative, so that's minus. And then it's another x, and then it's back to the derivative.
Holy
And
smoke.
because it's down at the bottom of here, there's an x squared.
Well, that's
Wow.
simple enough.
God,
Jeez. It was simple.
that was passed down
You
to
made
the
it.
Mayans on.
That's how I remember it.
Make it easier on
Sound
yourself.
like
dude.
that?
That's how my brain works. So
We have a little song, but I'm not gonna sing it. I'm gonna pretend I'm singing it, so there's my music.
What's your song?
It's my song, all right.
Oh, that's simple. No, it's fine.
Oh, wait, my calculus teachers did this.
Draw lines.
All good songs, rhyme.
Do-si-do. Below. Down, down.
Did you say do-si-do?
Oh, wow. I'm not able to run the denominator.
Denominator doesn't do rhymes.
Low D high minus high D low, draw a line and down below, denominator squared shall go. But that was back in my day when songs were kind of poppy. If you guys want to, put the little and kind of wrap it, then we wouldn't use a word
Can we
like
get
shout.
extra
We
credit if
would
we
just
can like
say
make like,
denominator squared go.
can we get extra credit if we make like EDM music based off of that?
That just means you've got way too much time on your hands.
Oh, no, I don't. I'm
Yeah.
constantly.
Right,
We don't
that
need
would
any-
almost be as bad as bringing a fake baby to class.
I know. I don't have to do that.
Have to? You mean you had to?
No,
That's hazing.
no, that's not what I said. Huh?
Put it down.
Oh, no, I dropped.
Squared formula is. Oh, we should like that.
You mean in statistics?
Sure. Yeah. You have like the observed minus the expected over the squared or something.
I'm not sure what, are you talking about an expected value in a chi-square distribution, maybe? I don't remember any of those formulas.
Well, it's just, so I'm in genetics and it's like the quotient rule looks kind of similar to like.
Yeah, I don't know.
I'm just trying to like make the connection to where like, one thing, or like the product rule kind of looks like a double angle.
I just think it's coincidental. I don't know. Okay, so let me give you another problem. Let's kind of put a little zing to it. Take that off. I guess I can take off my song. All right, so let's write the equation of the tangent line to the graph of f of x is equal to x plus 2 divided by 4x to the 1/3 minus 1 at the point where x is 1. So as you're writing it down, when you see this phrase, write an equation of the tangent line, I want you to have some sort of Pavlovian response. I want you to kind of foam at the mouth and kind of get a little shaky, thinking you're going to get a treat here. A good thing, right? You're going to get a piece of cheese. I'm going to get some cheese.
Dude, I love getting a piece of cheese.
But your mind is saying, take the derivative.
Right.
Equation of the tangent line, the derivative plays a role. What's the role of the derivative? Give us the slope. Then we're gonna write an equation, so we need the slope where? Well, we need it in x1, y1. And I've only given you the x1. So not only do you have to find the slope at that point, you're gonna have to find the y value at that point. Why don't we go ahead and get the y value first? Right? So what's the second member of the ordered pair? 1. It's 1, because if I put a 1 in here, I get 1 plus 2, 4 times the cube root of 1 minus 1. So I get 3 over 3 is equal to 1. So it's the ordered pair 1, 1. Then you told me that you need the derivative, so take the derivative. Go for it. Take the derivative and I'll catch up with you. Next, slope, tangent line is going to be the derivative. And x is 1. So take the derivative and then you'll put a 1 in for x. Yes, sir. I will, but that's not supposed to be an incentive.
No, like, it's something.
Yeah.
Sick.
Yeah.
So that's why I'm very much-
Sure, I put them on Blackboard. I usually count the number of people. And if there's less than 25, I'll try to get in the habit of starting this. So any of y'all, I'll put them on Blackboard. Or if there's any time that you're not gonna make it and you wanna zoom in, I also have this on Zoom.
Oh, okay, so that's like live right now?
So if you're laying in your bed, 9 o'clock, and you think, I'm not gonna walk way over there, zoom in and you'll see the same crap.
Is attendance counted in this class? I forgot.
Well, no, this is not high school. I don't count attendance.
But you should still go to class.
I don't care, and I don't give you a hall pass when you need to go potty. And
What? What did you do?
I don't know your locker combination.
This is one of the only 2 classes that I've classes.
Well, you paid good money for this. And let me tell you, I've been there, done that. So I've been through over a year of in-class or not in-person classes. And the Zooming thing just does not do
This
this.
should be other 2 classes. I don't see.
There's a point. There's a point. One point is you've got to network with your classmates and your professors.
I've networked pretty well.
Well, you've got to do it. You've got to be there to do it. Because every one of you is going to apply to some professional organization, work, graduate school, medical school. You're going to be there so that your professors know who you are.
You're gonna be our reference.
And didn't I tell you the story about how there's 2 people that are getting married that I had in Calculus 1? And I told you to start sniffing each other out?
Hello.
Really, Val?
I'm kind of nice today, baby.
Really, Val?
All right, so in all that, come to class because you're paying good money for it. You're getting professional instruction, give or take this class.
Are you looking for money?
I am going to do it next summer.
Summer wedding.
June, imagine that. Who gets married in June?
I wonder for the bachelor trip, they're gonna go to Vegas.
My dad told me yesterday, for the first time in my entire life, that he went to Vegas counting cars and like eight couple. That's pretty stuff. So like he went with $20 and left with like $2 from counting cars. And he told me to do this for like the first time yesterday.
If you get caught counting cars, you can be banned.
But if you get caught taking the derivative, you get that on that. So, take a
Yeah,
derivative.
guys.
The attention says, about 12.
I blame Val. He got us off topic first.
Because he's trying to figure out how to cut class.
Yeah, yes, you are, dude.
I'm just sorry. I'm just like, in this case, if I'm sick, but I get.
Well, I don't want you coming when you're sick.
Basically,
And nobody around
that
you
means-
wants you
that
coming when
means
you're
get out.
sick.
Yeah.
So you told me you were sick this morning and you still had the will to put on boots and jeans. I'm down and all of this week.
Very sick.
I'm gonna take the derivative.
But he went and got tested and he came back now. So.
All right, we're taking the derivative of this thing with the quotient rule,
Yes, ma'am.
and so there it is. We're gonna copy down the bottom factor. Then the derivative of the top factor is just gonna be 1. I'll put it here, but that's just baggage. Now we do it the other way, copy down the top factor
I think I done did it myself.
and take the derivative of the bottom.
It's not.
What did you guys get as the derivative of the bottom?
4/3 times the cube root of x squared.
Oh, give it to me in power form. 4,
Negative.
Bring the power
4
down.
thirds times x to the negative 2/3.
all right. The negative 2/3 is coming from 1 power less. So 1/3 minus 3/3 will give us the negative 2/3. And then we've got the bottom square. Now, if you're given a value that you need to evaluate the derivative, there's no reason to simplify in terms of x. Put the number in and then simplify. So let's find f prime at 1. If I put a 1 here, 1 to any power is 1. 4 minus 1 will give me 3. 3 times 1 is still 3. I'm going to put a 1 in here and I get a 3. And then 1 here. 1 to any power is 1, even if the power is negative. So this is just 1, so I've got a 4/3 here. Putting a 1 there, and I get 4 minus 1 is 3, so I have a 3 squared. So I get a negative 1 on top, right? The 3's will cancel, and a 9 on the bottom. So our slope is a negative 1/9. And now I've got m, x1, y1, put it in the point slope formula. Y minus y1 is equal to m times x minus x1. Both x1 and y1 were 1. We'll have y minus 1 is equal to that number, negative 1/9, x minus 1. And I don't care if we rearrange that in any order. It's okay? I can get way over here. There we go. All right. Let me see if you know what this means. Let's go with fractional exponents again. Let's just put a put 16 here. So you've seen this. That means the derivative of that. And so in this case, we take the 3/4 multiplied with the 16. What's 3/4 times 16?
Well,
Now I'm going to go 1 power less. 3/4 minus 4/4
negative 1/4.
gives me a negative 1/4. What do you think this means to do?
Do it again.
Do it again. Go to the derivative and take the derivative.
Wait, we never made the line.
Never made the line what?
Oh, we did.
I went from here to here.
I was slow.
So the two derivatives, the second derivative of f, take the derivative of this thing. So we bring the power down, multiply it with the 12, and now go 1 power less. So negative 1/4 minus 4/4
It's negative 5/4.
is negative 5/4. So if you're still having a good time, we can do it again. The third order derivative,
15/4.
15/4, and take 1 away from that x.
minus 9/4.
There you go. Now, if I put 4 slashes there, then people like me can't see it. I can't see that. We could go Roman numerals, but then again, we get into this, we're not from Rome. So if I want higher order derivatives, sometimes you'll see it like this. In parentheses, so you don't think it's a power. And that's the 4th derivative of f in terms of x. And so I have to take 9/4 times 15. It's going to be negative. 4 times 4 is 16. 90, 45 is 135. And then 1 fewer, so subtract 4/4 from that. And I get a negative 13/4. So we could do, in this example, derivatives forever.
Yes.
So when you see this, that's the nth order derivative. If we're using this notation, if we have some function here, and whatever the function's name is, suppose it's y, and y is equal to whatever, then we would write the first derivative as dy over dx. And so now if I want to take another derivative using that notation, I could write that, take the derivative of the derivative, but you'll see it written like this. Put the 2 next to the d, and then instead of writing that as dx all squared, we just write it as dx squared. It looks like the x is squared, but dx is a certain entity. So if I'm using that notation, then the order of the derivative is the number here, the name of the variable is there. So the nth order derivative would be dn y dxn. That's an alternative to using primes. That comes in handy because in calculus 3, you're going to do calculus to functions of several variables. So we can tell you how many derivatives to take and which variables to pay attention to. So if you have a function that has x, y's, and z's in it, you might see something like this. So if you have some function of x, y, and z, you might see something like d4 of f with respect to x, with respect to y, maybe you want 2 of those, and with respect to z. So you would one at a time take the derivatives. First derivative with respect to x, then you get an expression. Then you take a derivative with respect to y. Then you take that and take the derivative with respect to y again. Then you take that and take the derivative with respect to z. So that's why this notation is kind of handy as opposed to priming stuff. So you'll see functions of several variables. Take the derivative of f with respect to x, then the derivative of that with respect to y, then the derivative of that with respect to y again to get the second derivative, then the derivative of that with respect to z. So that's what you do in Cal 3. Same old stuff that you did in Cal 1, you just throw more variables in there. I guess I'm going to move that back to the other direction. Yep, that's the right arrow. But get used to seeing it written in any of the ways. Every now and then, not that often. Kind of in the old Cal 1, Cal 2 right? Because nobody else wants to teach Cal 1 and Cal 2. I get the leftovers. I am the bottom of the barrel.
Are they harder?
Do more fun. Oh, you mean the Cal 1 and Cal 2? Yeah, nobody wants to teach freshman.
Oh, that's what it is.
Type the numbers one teach upperclassmen. Like you guys have babies or something. You ask things like, when you come to class. Okay,
I'm sorry, what's WRT just right next?
with respect to,
Oh.
with respect to, you guys aren't at the window? The map window,
Yeah.
right, such that, I don't know, what are some other things that we use in math? Okay, there are other functions than just polynomial functions, right? We got boatload of trig functions. We got exponential functions and log functions. We need to learn how to take their derivatives. So I can take class time and show you how to take the derivatives using the definition. If I want to show you how to take the derivative of sine of x, I use sine of x plus h minus sine of x over h. Take the limit as h goes to 0. And then I've got to do a trig identity, got to do some more factoring, and show you what its derivative looks like. I'm kind of pressed for time, so I'm going to write down all the derivative rules. Maybe on Friday I'll go through all the derivatives. But today we'll write down the rules, we'll take the derivatives. Maybe on Friday I'll show you why they work.
George, can you tell us what's on the exam today?
I might.
Yes.
I want to see what you guys think of this. All right, so here's some more rules for finding derivatives, and it's in section 3. More rules for finding derivatives. Okay, so we have 6 trig functions. First one, sine of x. Found? Sine of x, cosine of x. Fine. The derivative with respect to x of the cosine of x is minus the sine of x. Now you're going to figure out the derivatives of the rest using the quotient rule. So let's do the quotient rule to get the derivative formula for the tangent of x. So I'll write it over there next, but here, if f of x is equal to the tangent of x, we can write the tangent of x as the sine of x over the cosine of x. And then use the quotient rule to find prime of x.
Sine pi of x minus, or sine pi of x cosine x minus cosine pi of x sine x over cosine.
There you go, do it. Do it. Do it on your paper while I erase. All right, so here we go. What's the quotient rule? The bottom times the derivative of the top minus the top times the derivative of the bottom squared. So the bottom is cosine of x. The derivative of the sine of x is cosine of x. Quotient rule has a minus here. The top is the sine of x. Now the derivative of the cosine of x is minus the sine of x. All over the bottom square. So I'm going to write cosine squared like that instead of cosine of x in parentheses squared. Okay, that point? Now when we multiply out the top, we get a cosine squared from here. I get a sine squared there, and 2 minuses give me a plus. Quick, what's cosine squared plus sine squared always add up to 1. Always adds up to 1. Which trig function is 1 over cosine? So this is secant squared. The derivative of tangent of x is the secant squared of x. All right, what's the reciprocal of the sine called? Cosecant. I want you to find the derivative of the cosecant by writing the cosecant as 1 over the sine and use the quotient rule. Yes, sir.
Okay, so I don't know why what this says. I think it's an derivative like this minus 3.
Uh-huh.
Is it bring it down to 0 or is it bring it down to nothing?
Well, you think of 3 as a constant, right? The derivative is the slope. What's the slope of a constant? Slope is 0.
So
So the derivative of any constant is 0.
okay, the value is 0.
Correct. Value is 0. All right, so here goes the quotient rule. All right, so here we go. Bottom times the derivative of the top. The top is just a constant, so its derivative is 0. Minus the top times the derivative of the bottom. From up there, the derivative of sine is a positive cosine. All over the bottom squared. So this simplifies, that multiplies to 0. I get a minus cosine of x over sine squared of x. That's going to be kind of hard to remember, so I'm going to write that as minus 1 over the sine of x times the cosine of x over the sine of x. So which two trig functions are being multiplied here? 1 over sine is the cosecant. Cosine over the sine is cotangent. So there's the derivative of cosecant. Minus the cosecant of x times the cotangent of x. All right, the reciprocal of the cosine is the secant. Yes.
Would it also be correct if there's like a negative cotangent?
Correct. Multiplication is commutative. So you can put that product in any order, just make sure you remember the minus sign. All right, this is going to work the same way, but we're going to have a 1 over cosine instead of a 1 over sine. So let's kind of scribble that one out real quick. All right, move over. Not down, over. Who hit the down button? Not me. All right, so for the same deal, I'm doing it this way in case you ever forget the formulas. You can figure it out like this. But you'll never forget the formulas because we're going to use them a gazillion times. But to take the derivative of the secant, you can write it as 1 over the cosine and use the quotient rule. So quotient rule, bottom times the derivative of the top. Top is a constant, so its derivative is 0. Minus the top times the derivative of the bottom. Negative sign all over the bottom squared. That first bit multiplies to 0. These two minuses will give me a positive sign of x on top. And then we do the same kind of factoring like we did there. Pull out a 1 over cosine of x and a sine x over cosine of x so that we have our trig reciprocal formulas. That's a secant, that's a tangent. Sorry? I would, at the end of the semester. So the derivative of secant is secant times the tangent. And one more fits down here. You can take the derivative of the cotangent by writing it as cosine over sine and doing the quotient rule. Back up to here. Move that back to there. F of x is equal to cotangent of x, which is the cosine of x over the sine of x. All right, here's the derivative. Bottom times the derivative of the top. The cosine is minus the sine. Minus the top times the derivative of the bottom. Derivative of sine is a positive cosine. All over the bottom square. When I multiply that out, you get a minus sine squared of x minus cosine squared of x over the sine squared of x. Okay with that? We'll factor out a -1. There's our favorite sum right there. Sine squared plus cosine squared is 1. So I've got a -1 on top. And that now is another trig function. 1 over sine was cosecant. So this represents a negative cosecant squared.
Will the test cover trig derivatives as well?
Because look how easy these are going to be remembered.
Oh, yeah.
There's a nice symmetry to it. This derivative and its co-function look alike. A derivative of tangent and a cotangent both have a squared trig function. Tangent goes with secant, cotangent goes with cosecant. These two guys are co-functions. The derivative of each of them has themselves in it and the other guy. The cotangent or the tangent has secants always go with tangents, cosecants always go with cotangents. Then the other thing that's neat is anything that begins with the letter C has a minus in its derivative.
What did you say that again? I'm sorry.
Any trig function that begins with the letter C has a minus in its derivative.
It's very nice.
Okay?
Yeah.
So if you can remember these three kind of fall in your lap because the other ones look just like them. Well, actually, you probably need to remember 4 of them, and the other 2 fall in your lap. Right? Minus cosecant cotangent, a secant tangent. Again, I'll show you why this is true with the definition here and here. These follow quotient rules. The next one, the easiest thing in the world is taking the derivative of e to the x. The derivative of e to the x is e to the x. It's the only function in the world whose derivative is itself.
I bet you can't figure out the 47th derivative of x.
That, how much money you want?
It's a terrible bad.
Remember, the e to the x is e to the x. Now, when you go through graduation 4 years from now, some of you 3 years from now, you're going to shake the president's hand who has a degree in mathematics. And he's going to see that you're an engineering or science student, and he's going to ask you, you know, what's your major, and you'll tell him, he'll say, what's the derivative of e to the x? If you don't get it, he's not going to give you your diploma.
It's like redo it 4 years.
So he did this to one chemical engineer. He goes, do you know the derivative of e to the x? And she goes, of course I do, and walked off.
Yeah, that's gonna tell.
Of course I do. So you've got to learn how to phrase it in the right way. The derivative of e to the x is e to the x. All right, I can prove it to you, but I'm not gonna. We're just gonna learn how to use them today. If inverse is the natural log of x, it has as its derivative 1 over x. The derivative of the natural log of x is 1 over x.
We asked him,
You can take his diploma away. All right, and so, start taking derivatives. All right, equation of the tangent line, how about that? The graph of f of x is equal to cotangent of x minus 2 times the cosecant of x at the point x is equal to, I don't know, how about 2 pi over 3. Thank gosh, we get to do some trig. So it's the same problem we did a minute ago, except for I changed the function. You're going to write an equation of a line. You know its line has a slope that's the derivative. You also need to know the y value that goes with the given x. So let's get that first. We need to evaluate the cotangent and the cosecant at 2 pi over 3, and then figure out that particular sum. First, find the y value that goes with this.
Wait.
We need f at 2 pi over 3, which is the cotangent of 2 pi over 3 minus cosecant of 2 pi over 3. So you need the cosine of 2 pi over 3 divided by the sine of 2 pi over 3 minus 2 over the sine of 2 pi over 3. Is there anybody in here who can get this number? A minute?
No, more than.
More than a minute. Well, firstly, 2 pi over 3 is an angle in which quadrant?
2.
Quadrant 2. In quadrant 2, which trig functions are positive? Sine, and it's reciprocal. The rest of them are negative. So you got a negative over a positive, 2 over a positive.
Negative.
All right, a reference angle is pi thirds. What's the cosine of pi thirds?
Wait, I need to write it right up the thingy.
Pi thirds is the same as 60 degrees,
1 or 1.
1/2. So this is going to be a negative 1/2. Now, when cosine's a half, what's the negative sign? Root 3 over 2. So this is a negative 1/2 over a positive square root of 3 over 2. So when I do the dividing, I flip and multiply. The halves will cancel. This is negative 1 over root 3 minus 2 over, 4 flip and multiply. 4 over root 3 for a grand total of minus 5 over root 3. That's the y1. That ain't no calculus right there. Let's do some calculus now.
So you don't care about rationalizing.
I don't care about rationalizing. Numbers, we don't do numbers. Take a derivative.
I left you way more than that high school calculus.
It's negative.
All right, so now I'm gonna take the derivative. You're gonna tell me what the derivative is. Right here at the cotangent. Take the derivative, cotangent of x. It has a c in it,
Negative
so I'm gonna start with a
cosecant
minus.
Square.
Yeah. Tangents and cotangents have trig functions that are squared. So negative cosecant squared goes with the cotangent. All right, next term also has a c in it, so its derivative is going to be negative. So I'm going to put a +2 here, and then a cosecant and a secant have themselves in their derivative. And then the other trig function would be a cotangent. Agree with that as the derivative? Now we have to evaluate that when x is 2 pi over 3.
I get it, yeah.
So we found the cosecant of 2 pi over 3. The cosecant of 2 pi over 3 was, where'd it go?
Negative 4 pi
But I
over.
don't want the 4, I just want the, this will be a 1, so it'll be 2 over the square root of 3, right?
Yeah.
So I got a minus, this is gonna be 2 over the square root of 3,
Wasn't it squared though?
and then it's squared. The minus sign is not squared, just the value. All right, so again, cosecant was 2 over the square root of 3. Cotangent is this number, and so that was negative 1 over square root of 3. Cosecant is 1 over the sine. So sine of 2 pi over 3 is square root of 3 over 2. Flip it over is 2 over the square root of 3. All right, so when I square the square roots of 3, I'm going to get 3. So this number is a negative 4/3. That's negative 2 times 2 gives me a negative 4 over 3. So I get a negative 8/3 as my slope.
It's a minus, you know, to do the thing.
Don't have to do the thing. The thing.
The multiply. A little. Have to be the real. That's the side.
I'm going to write down my tangent line now. Y minus y1 is m x minus x1. We've got my x1. We've got my y1. And we got our m. We just fill it in. Y minus a negative 5 over root 3 is equal to negative 8/3 x minus 2 pi. Okay. All right, so I'm going to ask that you practice these. Then I'm also going to ask is, what's your preference? This is section 3.3. We didn't do a heck of a lot of class examples. Do you want these on test 1 or on test 2?
That's two.
Test two.
You might regret that
What? Wait, why would we regret?
Test two's gonna be
because
hard.
test 2 has applications of the derivative and more.
We have a week though.
We have like,
We have 5 days.
yeah, but
I'm gonna let you decide. Exam 1 is going to be Monday.
I haven't even thought about studying for that yet. Just
Monday is going to be September, what? 20?
20th, yeah.
So I'm barely going to ask you anything over chapter 1.
What's chapter 1?
Chapter 2 had our stuff with limits and continuity. And then 3.1 was the definition of the derivative. And then 3.2 were derivatives of non-transcendental functions, just derivatives of polynomials. And if you want 3.3 on there, I'll put it. If you don't, I won't.
So could you weigh the pros and cons of having it on exam 1 and exam 2?
The first one would be easier.
I don't. You guys can barely even rate. I haven't put up a 3-3 web work yet, so maybe it makes sense for me just to stop at 2-2.
Yeah, we're not gonna practice.
So let's go to there. And I will put a review sheet on Blackboard, and I will put a 3-3 homework on Webwork. And we'll review on Friday, so if you've got a chance to look at the review sheet on Blackboard, that would be preferred. At least go through it and look at the outline, and then you can practice the problems on it. I want everybody to do well on the first test, so it makes sense to stop at 3-2. And then I'll nail you on the second one. I'm kidding. Everybody in honors calculus makes A's that wants A's.
Yes.
That's a challenge. That is absolutely a challenge. If you want an A, you can make an A in here. All right, let me end this. End the Zoomer.